that you've seen a little bit more about the 2-to-1 machine and the 3-to-1 machine and read about that, I want to give you a few thoughts about how to convert back and forth and a little bit about the count. So this 2-to-1 machine, I want to start referring to it as a counting system or numeration system referred to as base 2. Now, this is a pretty common base in the computer world because we call it something that's pretty familiar maybe to you, binary or binary code. So in binary or base 2, there are exactly 2 digits. So the digits for this base, you only have 2 options. You can either have a 0, that means no dots in a place value or a box, or you can have 1. And those are the only 2 digits. This entire code is written using just 2 digits, 0 and 1. And binary just has those 2 digits, and it's kind of useful in computers because you can kind of think of it electrically as either on or off in a very basic way. So let's take a little bit more, let's take a look at it more of this now that you have an understanding about the place values. So the place all the way to the right in any base will be the ones place. Now, rather than writing out these words, I might just denote it with a 1. And then you have the 2's place and the 4's place, the 8's place, and the 16's place. Now, those numbers don't all exist in binary. In fact, the only one that does is 1 because it only uses the digits 0 and 1. But those are reminders of the value for us because we're used to base 10. An example would be if I were to take a number in base 10, like, well, let's look at 14. If I were to put 14 dots in the right-hand side and go through the machine of the explosions and so on, I could come up with a base 2 code or a binary code. But if we know the place values, we can actually do something a little more powerful. We can try to build this number. Now, what you do is you look at the place values and decide which is the largest one that does not exceed 14. In this case, it's 8. If you go to 16, that's more than 14. So what you can do is put 1 dot in that box. That would have a value of 8. Go to the next box over. If you put a dot there, that has a value of 4. And 8 plus 4 is 12. If we're trying to build 14, I'm close. I'm only 2 away. So if I add 1 more dot in the 2's place, now I have a value of 8 plus 4 plus 2, which is actually 14. So that means if I do 1 here, 1 here, 1 here, and 0 in the 1's place, it's equivalent to 14. And so that's my code, 1, 1, 1, 0, base 2. And you can see that that could be a lot more powerful and quicker than exploding dots, particularly when there's lots of dots. Now, you can also use this idea to work backwards. If I were to give you a number in base 2, you can work backwards and put it into base 10. Really, it's kind of working forwards because it's moving to your native language, which is base 10, the one that we all learned in school. So let's take a look at an example of that. I want to look at the number 10001 base 2. Notice it's only made out of 0s and 1s. That would mean I have 1 dot over in the 16's place, right? 0, 0, 0, and then 1 dot in the 1's place. So what is its total value? We can just look at the place value. The dot all the way to the left is worth 16. The dot all the way to the right is worth 1. 16 and 1 is a value of 17. So that means that this number is equal to 17. Now, to take this just a little bit further, I want to talk a little bit about the count. The count would be how this numeration system sounds as we count it aloud. Okay, so this, you might have to rewind this part or think about it a little bit more. But once you get the hang of it, it's not too bad. So the count, the first number would be 1. Well, any counting system, we start with 1. We do as well, 1, 2, 3, 4, 5, and so on. Okay, in base 2, though, there is no 2. Remember, there's only the digits of 0 and 1. So if you put a second dot, remember those 2 dots would combine, explode, and move to the left. So our next number is 1, 0. And then we would have 1, 1. Then we would have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and finally 1, 0, 0, 0. Notice the numbers are expanding or getting wide really quickly. Continuing on, we would then have 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, and finally 1, 0, 0, 0, 0. So it's getting really wide. The next number, we would just add 1 more, 1, 0, 0, 0, 1. Now that was time consuming, but here's the point I want to make. In this count, it sounds really hard to this is base 2 counting. I want to note that, right? These are base 2 numbers. I didn't write the TWO, but imagine that all base 2. Notice how it would match up to our base 10 system. Let's kind of take it number by number and see that. So if we count in base 10 and then touch those digits at the same time, it's going to look something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17, what did we learn? We learned that the 17th number in base 2 is 10001. Well, look back to what we did over here. You can see a perfect match there. In other words, the count will match what we do numerically to go back and forth. Okay, you're going to meditate on that. We're going to ask you a few questions about that. Let's also look at base 3. We've been calling it a 3-to-1 machine, but I want to refer to it as base 3. Now, base 3, like base 2, starts with the ones place, but then since it takes 3 dots, we're going to then have the threes place. 3 3s makes the 9s place. 3 9s makes the 27s place. 3 27s makes the 81st place. And something I want to note about this, even though I've run out of boxes, these would continue indefinitely to the left if the numbers got larger and larger and larger. So the next place, by the way, that we don't have listed, if we were to draw it in, well, I could draw it in. I could add one more box, would just be 81 times 3. And then whatever that number is, which I believe it would be 243. 243, we could multiply again by 3 and continue forever indefinitely to the left. So in base 3, we can use the same strategy. If I give you a number like, let's see, I'm going to do 32. If you want to build a value of 32, you just think about what's the very largest number that doesn't exceed 32. That's 27. Put a dot there. That's 27. Now, if I put a dot in the next place, in the 9's place, that's not going to work because 27 plus 9 is already 36. That's too much. Can't put a dot there. I can put a dot there. 27 plus 3 is 30. And then put a dot there, 31. But since I'm in base 3, I'm actually allowed up to 2 dots. One more makes 32. So this code would be 1012 in base 3. So the digits in base 3, I haven't written those yet, but the digits are all, the number of digits are always equal to the base. So since we have base 3, we're now up to 3 digits. We can have a 0, no dots, 1 dot, or 2 dots. Those are our 3 different digits. We get 1 extra digit over base 2. You can use the same idea we did earlier to take a number in base 3 and take it back to base 10. So an example of that would be something like, well, if I ask you 20121 base 3, what is that in base 10 or in a regular numbering system? You don't have to draw the dots, but this is basically what it's saying. You have 2 dots in the 81's place. That's my 2 there. You have 0 dots in the next place. You have 1 dot in the 9's place. You have 2 dots in the 3's place. And finally, you have 1 dot in the 1's place. To find the total value, you're just taking the sum of all of that. And so to write it, I'll write it out for you, but you could use a calculator as well. We have 2 81s, so we're going to have to figure out what 2 times 81 is. We have no 27s, and I'll just put 0 there. We have 1 9. I'll do that in my head. 1 times 9 is 9. And then we have 2 3s. All right, I'll write 2 times 3, although we could do that in our head. And then we have 1 1. That is going to be our total value. So if you have a calculator, you can do that. If you want to use do it by hand, you can do that as well. I'm just going to use the calculator so I don't mess up on this video. So 2 times 81, 162. So the first term is 162. We're going to add 0. We're going to add 9. We're going to add 6. And we're going to add 1. That's the numbers from the left to the right. So that would have a value of 178. Now, I'm not going to prove this, but what that means is if I were to count in base 3, by the time I got up to the number 20121 base 3, that would be the 178th number. But since we're here, let's do a little bit of the count so you can kind of get the feel for it. So the count will look similar to base 2, but we're going to expand it out because we have 3 digits. This time I'm going to organize my count a little bit so you can see it out. It might remind you of a hundreds chart when you counted in elementary school. So the count looks something like this. 1, 2, What's the next number? Now it feels like it might be 3, but it's not because there is no 3 in base 3. So the answer is you have to move over a place value, it becomes 1, 0. So sometimes when I teach this face-to-face and we're counting out loud in class, I would say, remember in elementary school when you would say something like this, 32, 33, 34, 35, 36, 37, 38, 39. You would kind of go up, right? That's what we learned in elementary. And then you would say 40. So in this count, it would sound something like this: 1, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. It's tempting to put 3, 0. Remember, there's no 3. So you have to move over a place value, 1, 0, 0. And then it would continue. I'm kind of, instead of doing commas, I'm just kind of stacking these so you can hopefully see a pattern. 1, 0, 1, 1, 0, 2, 1, 1, 0, 1, 1, 1, 1, 1, 2, 1, 2, 0, 1, 2, 1, 1, 2, 2, 2, 0, 0. Maybe you're getting the hang of it so far. Then we go on 2, 0, 1, 2, 0, 2, 2, 1, 0, and then so on and so on. If we kept counting the numbers, we could eventually see how the ones we've already done would match up. But just give you a small example. If I were to count these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I'll stop there. The 11th number in base 3, so the 11th number in base 3 is 102. That means for us, it's equal to 11. That may seem a little strange at first, and you might need to think about that, but let me just show you quickly how that would work before this video ends in the box. So why is 102 base 3 equal to 11? Well, let's use our guide here. Let me just erase some of the stuff we have in these boxes. And this time it was just a 3-digit number, right? 102. So looking at it, we have 102, but remember in base 3, 1's place, 3's place, 9's place. We have 1 dot here, no dots, and 2 dots. So notice we have 1, 9, so that's the value of 9, plus 2 more, 2 1s, and 9 plus 2 is actually 11. So sure enough, we can see that that was verified, that 11 is equal to 102 base 3. All right, time for you to practice.